So now we're going to look at the areas of similar triangles. In that, how are they related? Now obviously we know that for congruent triangles, the areas are just equal because they're the exact same thing. So obviously the area will be equal. Similar triangles is not so obvious. And in fact, before I tell you what the result is, let's derive it together because that way you will always remember it. So let's say I have two triangles, a triangle ABC and a triangle PQR, and it is given to me that triangle ABC is similar to triangle PQR. And I am asked to find the ratio of the areas of triangle ABC and triangle PQR. So we are going to find the ratio of the area of triangle ABC upon the area of triangle PQR. Now when we're talking about triangles, we know that we simply have to use half base into height. And so if I imagine that I draw a perpendicular AD in my ABC triangle and I draw a perpendicular PM in my PQR triangle, that means what I have to find is nothing but, when I say area of triangle ABC upon area of triangle PQR, I will be getting half into BC into AD divided by half into QR into PM, which I can notice that I can cancel my half and half and I am left with BC into AD upon QR into PM. Now you might think that this is it, this is the result, that oh okay fine, the ratio of the areas is just base into height. But that doesn't give us anything, that's the ratio of any two triangles' areas. What we are going to show is we can get rid of this AP upon PM, this AD upon PM by analyzing our figure. Now if it is given that triangle ABC is similar to triangle PQR, then if I consider triangle ABD, just keep it in the frame, if I look at in triangle ABD and triangle PQM, angle B will be equal to angle Q. Because ABC is similar to PQR, their corresponding angles will be equal. So angle B is equal to angle Q. Obviously angle D is equal to angle M. Once again they are 90 degrees. This comes from CPST from triangle ABC similar to triangle PQR, and therefore by AA similarity we end up getting triangle ABD is similar to triangle PQM, which we by again AA similarity. Why did we do this? Because now I can see that if the triangles are similar, then what we'll end up getting is I can use my triangles to find a relationship between the ratios of the sides, right? And what I have over here is this will imply that AB upon PQ is equal to AD upon PM, which is what I had over here. Now if I have AB upon PQ equal to AD upon PM, we also know that AB upon PQ is equal to BC upon QR is equal to AC upon PR, because again in triangles ABC and triangle PQR, by CPST we'll get AB upon PQ is equal to BC upon QR is equal to AC upon PR is equal to AD upon PM. And if that means, that obviously means BC upon QR is equal to AD upon PM. And so I am going to go and plug that into my formula for the ratio of the areas. I will replace AD upon PM with BC upon QR. So I end up getting that area of triangle ABC divided by area of triangle PQR is equal to BC upon QR into BC upon QR, which is nothing but BC upon QR whole square. And since we know that the ratio of all the sides are equal, we see that the result that we get is that the area ratio of two similar triangles is nothing but the square of the ratios of the sides. So it's AB upon PQ square also equal to BC upon QR square also equal to AC upon PR squared. So ratio of the areas of a triangle of two similar triangles is equal to the square of the ratio of the sides. So again, the proof needs to be learnt because it can come as a question in the exam, and also the result is important because we will solve a couple of questions. So let's do that and then move on to the final part of the chapter, which is using Rhs similarity and Pythagoras theorem. So now let's look at a question where we will use this relationship between the area and the sides. We are given that XY is parallel to AC in triangle ABC. It is also given that XY divides triangle ABC into two equal parts. Obviously, that means area of XBY is equal to area of AXYC, or it means that the very first thing is that area of XBY is equal to half the area of ABC. Obviously, if it's two equal parts, one part will be half of the big part. Now, they've asked us to find the ratio AX is to AB. So to do that, we will start by first finding the ratio XB is to AB. Why? Because if I know that the area of triangle XBY is equal to half the area of triangle ABC, this obviously means area of triangle XBY upon area of triangle ABC is equal to 1 by 2. So since I have a ratio of the areas, I can find a ratio of the sides. And of course, triangles XBY and ABC will obviously be similar, because in triangle XBY and triangle ABC, we will basically use the fact that since XY is parallel to, so in triangle XBY and triangle ABC, we have angle A, angle B equal to angle B common. And then you can take any other side. So I'm going to, in this case, take angle XYB equal to angle ACB, because they are nothing but corresponding angles of parallel lines. Corresponding angles. Right? Because obviously if XY is parallel to AC, XY and angle Y and angle C are corresponding angles. Now they're corresponding angles, and therefore this means that triangle XBY is similar to triangle ABC by again AA similarity, which means that the ratio of the areas will be equal to the square of the ratio of the side. And like I said, I'm going to use XB and AB because I want AX and AB. Now, is equal to XB upon AB whole square, which is of course equal to nothing but 1 by 2. So now if XB upon AB whole square is equal to 1 by 2, that means that XB upon AB square is equal to 1 by 2. So if I take square root on both sides, I'll get XB upon AB is equal to 1 by root 2. Now what we wanted to find was actually AX upon AB. If we look at it, AX is nothing but AB minus XB, and I can create AB minus XB by subtracting both sides from 1. So if this is true, then I'll say subtracting both sides by 1, we'll get 1 minus XB upon AB is equal to 1 by root 2 or 1 minus 1 by root 2, which means AB minus XB upon AB is equal to root 2 minus 1 upon root 2, and as I said, AB minus XB will be nothing but AX. So we'll get AX upon AB is equal to root 2 minus 1 upon root 2. And this is another important question. This skill that we just did, where we find the ratio of two sides and then add or subtract 1, will be used by you in many questions where you'll find yourself finding a ratio but not the exact one you want. So you'll observe, see what is the bigger side, see what you want to subtract, and proceed from there. And so, like I said, this is an application of the area. We found the ratio of the area. From there we found the ratio of the sides, nothing but the square root of the area, because area is square of the sides, and then manipulated our result to get to what we want. These are things that will come with practice. Initially they might seem daunting, they might seem, you might think, how will I think of it in the exam? But when you've done enough questions, it will come naturally to you. So let's look at a couple more and then move on. So now we're going to look at a question which is actually a trick question. It is an area question, but one in which we will not be using the square formula. The question is that we have a trapezium ABCD in which the diagonals AC and BD intersect at O. And we have been asked to prove that the ratio of triangle ABD to triangle DBC is equal to AO upon CO. So you might be wondering, why is it that I said we will not use the square formula? Because if we see here, it's not a square. And if it's not a square, how will the square formula work? Which is why what we do in this question is we drop a perpendicular from A to BD, let it be AM, and from C to BD, let it be CN. And so, like I said, we have this construction that we draw AM perpendicular to BD and CN perpendicular to BD. Because now if I start with the proof, I'll see that area of triangle ABD upon area of triangle DBC will be nothing but half into BD, because that is the base I'm going to take for triangle ABD, into AM upon half into DB again, because I'm going to take DB for DBC, so BD, into CN. And so I see that not only do half and half get cut, even BD and BD get cut. So I'm left with that the ratio of the areas of my required triangles is AM upon CN. But it wanted us to show AO upon CO. That is very easy. We have done questions like this now. All we need to do is see that if I want to get AO upon CO, I'll look at triangle AOM and CON. Because they have vertically opposite angles. They have 90 degrees, 90 degrees. So they will be similar by AA, and then the ratios of the sides will be equal. So simply writing it out, in triangle AOM and triangle CON, angle AOM is equal to angle CON, vertically opposite angles. Angle AMO is equal to angle CNO, both are 90 degrees, which means by AA, triangle AOM is similar to triangle CON, which means that AO upon CO is equal to AM upon CN. And so, since I found that the ratio of my triangle's area was triangle ABD upon area of triangle DBC was AM upon CN, that means it's also equal to AO upon CO, which is what we wanted to prove. So you always have to be very careful about what exactly is the question asking. You can't just assume that, oh, it's talking about areas, must mean ratio of areas. So that is how we approach it. Let's look at a last question in which we will be using the area formula. So now there's a question which I'm going to explain it to you verbally before we start solving it. The question says that we have to show that the ratio of the area of a triangle described on the side of a square to the area of the triangle described on a diagonal of the square, equilateral triangles, that the ratio of their areas is half. I'll be pasting the question as well so that you people can see it very clearly. But the idea is that they say that these are equilateral triangles described on the side and diagonal of a square. When we say a figure is described on something, it means the thing it is described on makes up part of your figure. So what it means is that if I talk about a square, if they say a triangle, an equilateral triangle described on the side of a square, they try to say that it's an equilateral triangle with the side of the square being one of the sides of your equilateral triangle, meaning it is like this. That this will be one of your equilateral triangles. And the equilateral triangle described on the diagonal will be like this. You can think about it, since this angle is 45, obviously the sides of the triangle will come out a little bit. So in other words, what they've simply asked us to prove is that if, let's say, this is a square PQRS and let these be 2 points A and B, we have to prove that area of triangle APQ upon area of triangle QBS is equal to half. This is what we have to prove. So the approach is very, very simple. It is given to us that these are both equilateral triangles. If they are equilateral triangles, all angles are 60 degrees. So in triangles APQ and triangle QBS area. So we know that angle P is equal to, you can take anything, angle Q, angle A is equal to angle B, and angle Q is equal to angle S, because they are all 60 degrees because they are equilateral triangles. And therefore, by AA similarity, or in this case even AAA, but simply by AA similarity, triangle APQ is similar to triangle PQBS. Now that means that the area of triangle APQ upon the area of triangle QBS will be equal to, I'm going to use PQ and QS. Because it's an equilateral triangle, I can take whatever I want. PQ upon QS whole square. Now if we actually come to the triangle itself, if I assume PQ is X, that means PS is also X because it's a square. If it's a square, this is 90 degrees. So I can get QS in terms of PQ. So in triangle, as we had over there, PQS, PQ square plus QS square, PQ square plus PS square, PQ square plus PS square is equal to QS square, which means X square plus X square is equal to QS square, and so that means QS square is equal to 2x square, which means QS is equal to root 2x, and therefore when I plug it into my ratio of the areas, area of triangle APQ upon area of triangle QBS is equal to, we had PQ upon QS whole square, which is nothing but PQ square upon QS square, which will be X square upon root 2x square or 2x square, because we already had that here, which is 1 by 2, which is what the question asked for. So in this case, the only thing to understand in this question is that when they say described on the side, they just mean it's an equilateral triangle on the side of the square. So the side of the square is one of the sides of the triangle. For the other one, the diagonal is one of the sides. Equilateral triangles, all angles are 60. They're completely similar, and therefore we simply use the square of the sides. The square of the sides, we have a relationship, and we solve it from there. So like this, you will tackle area questions, improve similar, take appropriate sides, and solve. Other than that, we're left with just RHS and Pythagoras theorem. We'll finish that off and then finish the chapter.